So as we get started, don't be fooled by that slide. What I wanted to do before we get too far is just kind of go make sure that we have a decent grasp of what area moment of inertia is. It's a really, really important concept that it's going to come back again and again and again and again. So we just want to make sure that we got it pretty well to start off with. I was explaining it, how I was explaining it last class, is that say that you have a sheet of cardstock, like this folder thing, and you bend it across that, which is called one axis. So I'm bending it like this. Then I say, well, that's fun, but what if I take that same sheet of paper and I bend it around that axis? It's called, it acts a little bit it's called acts a little bit it's called a little bit different, it's called a little bit differently. If you bend it across each, you can kind of feel that there's a little bit more resistance one way than the other. So bending it like that versus like that, and the material itself hasn't changed, right? Its material properties are constant. It's all the same stiffnesses, all the same strengths, all the same stuff. And I'm going to need that back in a sec whenever you're done with it, please. Thanks. But it's called how stiff it is has changed depending on what direction I'm bending it in. So the only thing about the material itself that has changed from one axis to another, thanks, Santa, is the distribution of the material itself along those two axes. Perpendicular to those two axes. Like if I cut a cross section through here, I'll encounter less material, say, than through here. So it might be intuitive that where there's more material, it's harder to bend. So that's one way of looking at an area moment of inertia. You can also think of these two axes as kind of like your x-axis and your y-axis, and the area moment of inertia associated with that would be like IYY, or some people call it IY. You'll see both notations. And same thing for bending around the x-axis. And so the measure of that area distribution, the measure of how material is distributed along the cross section, is called the second moment of area, and that's what these things are. Now, to get to the polar moment of inertia, which is what we've been looking at more recently, you might imagine that if these two area moments of inertia describe how material is distributed along a cross section, then a polar moment of inertia, which if I drew like an out of the page axis, like a z-axis, and that axis corresponds to trying to twist this thing this way, kind of bend it around that axis. You might imagine that area distribution is going to be some combination of these two, because it deals with the entire plane of the piece of paper. It deals with the entire piece of paper instead of just a cross section of it. So that's where we had gone before. So all these axes go through the same point. So I can say that the polar moment of inertia, J, is equal to the sum of my two in-plane area moment of inertias on axes that go through the same point that the axis of the polar moment of inertia go through. All right, are we Happy with that explanation, or is every moment of inertia still kind of weird and odd thing? Say again.
Still weird.
Still weird. Okay, how so? So this is just always weird. Okay, well I can deal with that. Okay, so that's so it's called. I just wanted to go through that again. That's area, which called that's what's called area moments of inertia, and how they're a polar moment of inertia, and just what those kind of physically mean. Okay, so if we're good with that, we'll continue on for the rest of the day. Okay, I think it was around 15. Nope, a little earlier, a little later. Okay, so last week we were talking a little bit about how brittle and ductile materials fail in torsion. That is. Do you guys remember which one of these corresponds to a brittle material? Which one corresponds to a ductile failure? Which one corresponds to a brittle failure? Brittles. Say again. Okay, so we have one vote for each. Sweet, someone must be right. Why? Why each? Why brittle on top? Why ductile on top?
Well, I broke a lot of taps over the summer.
Touche. Hey, so you broke a lot of screws, essentially. Okay, and they come out with a flat face. Okay, that's actually interesting, because taps should be really brittle, but I don't know. Anyhow, okay, so I'm going to throw these into the ring again. My old Jeep's oil pans and plug and a quarter 20 screw. You make your own cold. You make your own cold brew. Nice. So those both are made out of stainless steel. Stainless steel is a ductile material. Both of those have failed with a virtually flat face. So we can tell, just empirically speaking, that our intuition from how things fail in tension does not hold in torsion, and a flat face, a flat break is actually the indication of a ductile failure, and a kind of like a 45-degree break is a symptom of a brittle material that has just failed. And the question as to why kind of takes us back to when we were looking at different orientations of a stress cube, or different planes and the stresses on those planes. So I'll jump back over to here. Trying to take this apart without breaking it more. If we look back to something that's failing in compression, we see that we get what's called an angled failure, which call an angled failure per plane. So if I have a rod, I put it into tension, and I look at a cube. I look at a little stress cube inside of it. So I zoom in on that and look at the forces acting on it. And just ignore the rest of this for a second. There is this larger material thing that hopefully I can draw. But we're just going to, it exists, but we're just going to focus on a little chunk of material on the inside. So if I just look at this material, what forces are acting on it? Are there any forces acting on it?
Yeah.
Yes. Good answer. What are they? Let me just write some numbers here so it looks nicer. What force is acting on that little guy in the center? Say again? Okay. Why? Just because, yes. So, as he saw a couple weeks ago, if I just have a uniform brick and I start pulling on both sides of it, that force is going to uniformly distribute itself throughout the entire brick, if you will, throughout the entire structure. In order to transmit 10 pounds from here to here, from the top to the bottom, every bit inside of that brick also has to feel that 10 pounds in some way, shape, or form. So we know that this little element here also has to feel the same state of stresses, same forces as the rest of the thing. However, if we take a different brick, say, I'm going to arbitrarily draw one that's oriented at a 45-degree angle here. That same force of 10 pounds, so you still have a 10-pound thing here, 10-pound load, is going to create different shear forces and different normal forces on this brick, right? Because I can decompose that 10-pound vector into two. That blue doesn't show up very well, does it? Into two other vectors that are respectively perpendicular and parallel to the face of that stress cube, right? And we've done all that in homeworks and all that kind of jazz. So I'm not going to rehash it here. And from here we get different shear stresses and normal stresses than if we had a normally oriented shear cube. And we said, okay, in what's called inductive materials, they're more sensitive to shear stress. So as that so they'll fail on that maximum shear plane, which is at a 45 degrees. It's at 45 degrees to the long axis of the material, at least when you have tension and compression loading, and that's why you get these angled breaks, some which are really darn close to 45 degrees. However, in torsion, it's a little bit different. So just ignore this for a second. Ignore this half. There's a torque there. So we have Newton's third law being happy with us. If we just look at a stress cube oriented normally to the long axis, meaning that it's, which you can say that it's oriented parallel to the long axis if you want, and you have a torque on this. If we look at any cross section, you could kind of have imagined that if each cross section is in shear, so the forces are parallel to the face, then we can also draw some forces on this stress cube. And in order to balance those forces, we have to have a corresponding what's called a corresponding couple on the other two faces. So that cube is currently in pure shear. So if ductile materials are most sensitive to shear, and the pure shear state is when the stress cube is oriented parallel to the long axis, that would also correspond to how those bolts broke along a flat face parallel to the edges of that parallel to the edges of that stress cube. Does that make sense? Are we following with how brittle materials fail? Cool. Sort of, kind of. Okay, getting some mixed nods. Let's try this. So, if that's a brittle failure, so that's a ductile failure, because that's the maximum shear state. What how would I orient that stress cube in order to get a normal stress acting on that cube? Okay, so I have a cube that I erased here that's oriented at some angle. What angle would it be at? Should be at 45 degrees. So for the same reasons as with that stress cube that's what's called on the brick that I'm pulling in tension or pushing in compression, giving me which called that gave me a transformation from purely normal stresses to pure shear stresses. I can do the same thing here and go from pure shear to a pure normal stress, and put this element entirely in tension, which we know is how brittle materials break. And since that state of stress occurs when you have occurs on a plane that's angled at 45 degrees to the long axis of the material, that's how you end up with these kind of helical spiral breaks for brittle materials in torsion, as opposed to these flat faces in for ductile materials. All right, so quick recap of that. You happy with that? Happy enough? Cool. All right, so let's move on then. So we talked about how things break, stresses, the material, and all that jazz. Let's start looking at strain. So this is kind of like the same sort of progression as we had in normal stress. So this is from a couple weeks ago or last week or something like that. I don't know. It's all kind of blended in together. Expression for the maximum shear strain in torsion. So we said that that's if we have a little element sitting here that's not deformed. We haven't done anything with the beam yet. Then we twist it, and it's going to want to follow the deformation of the rod as it twists, which means that because we've made some small angles assumptions and whatnot, the two sides, like this side and this side, are going to remain parallel. It's just the top and the bottom that are going to kind of twist with the rod. So strain we can measure as the angle of the angle of deflection there, and a measure of that, and that's going to depend on where we are along the rod. So L, along its length. It's going to depend on the radius of the rod, which our book uses C for, because we can pick any arbitrary radius from 0 to the outside of the shaft of the rod, whatever you want to call it. And the angle of twist, phi. And the angle of twist is if I drew a line along the rod and watched where it displaced to. So it started out at A and it moves to A prime. The angle that it moves through, phi, is the so-called angle of twist for the rod. So you might think of it as like the maximum shear, if you will, because it kind of is, sort of. Anyhow, okay, so we had this from last time, but it's not really related to stress. So let's do some math. Yay. We're trying to find an expression for this angle of twist, because at the end of the day, say that I'm making say that I'm making a system where I need to know the relationship between a handle that I'm turning and, say, the position of a table that it's moving with some sort of like a leads with some sort of like a lead screw or something like that. Like if you ever turned turn the handle and it moves it moves a table or a shaft, it goes along the same principle. It's how all these 3D printers work. So you might imagine that if you're trying to be very precise about things, you're trying to measure something, knowing how much give there is going to be really important. Sure, for some applications you probably don't care. Like if I'm just making something to roughly align crap, whatever. But say that I'm making a table for a mill or a 3D printer where you have to care about thousandths of an inch. This starts to get a little bit important. So instead of making precision machinery or whatever, it's important and stuff. So let's see what we can do. So if I'm trying to get an expression for phi, gamma max is kind of like it's a number and it's an important one, but it's not really directly related to something that I care about. Stuff that I care about, stuff that I can measure, are like torques, are like geometric things. So things like polar moment of inertia. They are material properties like the modulus of rigidity. So if I can somehow get stuff like that in this equation instead of a shear strain, that'd be a good thing. So we do know of an expression that has at least some of those in it. So how can I relate shear strain to stress? Okay, so it's called C over P times gamma, something like that. So that's just more strain, right? Gamma strain. But what about Hooke's law? What's Hooke's law in torsion?
Modulus of rigidity.
Times
Strength.
equals.
Stress.
Yay! Yeah. Shear stress specifically. And I know that the maximum shear stress occurs at the maximum shear strain. It's just Hooke's law in torsion, similar to Hooke's law in tension, where you have normal stress equals Young's modulus times normal strain. So I can solve all this for gamma max, and I get an expression for that maximum shear strain in terms of a maximum shear stress and the modulus of rigidity. Now, this guy is a material property, so I can find that. I can either say, hey, I'm making this thing out of steel. What's its modulus of rigidity? I'm making this out of wood. Blah, 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 blah. Read it out of the book. Tau max, I know that that's related to torque, right? From last class or whatever, we were saying that, was it TL over JG or something like that? TC over JG? TC over J. We know that tau max is equal to something like that. So it's related to the torque that's being that's being applied to the shaft. It's related to the radius of the shaft, C, and it's related to the geometric properties of the shaft for the polar moment of inertia, J. All right. So let's if I take that, just need a little bit more room. Substitute that in. So TC over J. I come up with this expression for the maximum shear strain. And that that and that I can work, and that I can work, and that I can work, and that I can work with, because that's a geometric property. That's a geometric property. If I'm designing to a particular torque, if I'm designing for a motor or a particular application, I can probably estimate whatever the torque is, or whatever the load is. And this is just a material property. So I can either solve for that, or I can read it out of a book for whatever material that I'm going to use. So this is good. We can use that. So let's rewrite. Get rid of some stuff here. TC over GJ. If I substitute that into here, I get TC over GJ, CP over L. Remember, I'm solving for that guy. So radii cancel out, and I get something like TL over GJ equal my angle of twist. Sweet. So now, given a shaft, a loading, and a material, I can get an angle of twist. Or kind of conversely, if I have a maximum allowed angle of twist, so the most that I want this shaft to deflect in torsion, I can go back and get what a maximum loading is, or what a maximum length is, or geometric properties, or material properties. Use it whatever way I want. Cool. So this is good, right? So let's kind of put this to use. So your favorite friend, superposition. Works for stresses, works for strains, and all kinds. Let's call it. You've already used it for a normal stress problem. Got one coming up this week that kind of deals with the same thing. Now we're going to use it for strains, for what's called angles of twist, rather. Now the neat thing about superposition is that we're solving all what are called linear problems, meaning that we can make this shaft independent from this part of the shaft, independent from this part of the shaft, so long as we apply the same loadings at each intersection, at each section. So, like, for example, if I have this little gear set thing that's absolutely awesome, I can have all three gears here and turn them, and I get all three turning, and it's awesome and cool. Or if I say that I decide to apply some torque to the smallest gear, that of course transmits up to the big gear, right? If I apply some torque here, it's going to be transmitted to this guy here, transmitted to this guy here, blah 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 blah. Say that I remove that tiny gear. Now I can get the same effect by just applying however that torque is being transmitted from here to here, which is by the force between the gear teeth. If I just replace this gear with a corresponding force, the rest of the system doesn't care. It's seeing the same thing. So I can reduce this to just forces and torques that match the whole system, and I'll still get the same result. I'll still have the same physical effects. And that's exactly what we've been doing with the principle of superposition, and what we are going to do here. Instead of considering this whole set of gears at one time, we're going to say, well, let's start out ignoring all this stuff. We're just going to start from this end, start going left, and I can go from right to left instead of left to right. I just like left to right. You'll come out with the exact same answer. The exact same answer, I promise. You can do it if you want, and it'll work. And I can say, okay, what am I going to encounter along this particular section? Okay, I have a torque of that much. I have a torque of yay, which I have a torque of yay much. Eventually, I'm going to see the second one, but not yet because I'm going across here. So, I got a little bit ahead of myself. So if I draw that first bit, wow, I'm doing terrible with this. Okay. Wow, it looks like a caveman axe with a bone. So this is the first gear. I'm ignoring this too. Sorry. So I'm starting on this end. I'm going across. I'm saying I have this torque. I've gone right up virtually until that second pulley gear friction roller thing. I'm not quite. I'm infinitesimally close to it. I don't see it yet. I've kind of left off the rest of this. I've kind of left off the rest of this the rest of the system. So one could kind of take this in our gear analogy. So we're starting at the tiny gear. I'm saying I have such and such a torque. What's going to happen to this gear? And I can take this and say, okay, this end of the shaft has to react that torque in order to be in static equilibrium, right? So I know what torque is being reacted throughout this entire shaft. And what torque would that be?
6,000 meters.
Yeah. Equal and opposite, of course. So I know the torque through that entire shaft. I know a length. I do not know a diameter. It's something unknown. But I could specify a material property. I just have something realistic. Can you on the homework that you just turned in? I think I had that I just handed back to you. Rather, I think I had you who find modulus of rigidity for the first one, or the second one. Could someone just give me their number for it, please?
27.8 gigapascal.
Thank you. Just have something somewhat realistic to work with here. So that's lots of modulus of rigidity for aluminum, I believe.
Yep.
We have 6061 aluminum, pretty standard grade. So we have modulus of rigidity, we have a torque, we have a length. If I'm looking at the equation for angle of twist, excuse me. Excuse me. I'm looking at the equation for angle of twist. TL over JG. I'm also going to specify that this shaft can twist no more than a tenth of a degree in order to keep the a hundredth of a degree in order to keep the precision in order to maintain the precision in the system. So another way of saying that would be like a maximum angle of twist would be 0.01 degrees. Okay, so I have all this data. How do I figure out the diameter of the shaft that will yield that maximum angle of twist? solve for J. Why J? What's in J? Pi r to the fourth over 2, right? Because for a solid shaft, we know that, we know that the polar moment of inertia is given as a function of the radius to the fourth power. So if we rearrange this thing, where am I here? Okay, do a bunch of math. So say pi over 2 r to the fourth equals TL over phi g. Move back up. Erase a little bit of that, sorry. Say r to the fourth equals 2 over pi TL over phi g, and take the fourth root of that. And cool, I get radius. And if I multiply by 2, I get, what you call it, diameter, right? So, cool. So what do we get out for that? Make sure that you expand, or that you're consistent with your units. We have a giga, so a 10 to the 9th here, and a kilo, 10 to the 3rd. So make sure that all your units jive. And this degrees should also, it's called, degrees don't do any good in computation, so radians are your best friend. Yeah, you and your TI-89. Hundredth of a degree. It's like 0.01 times pi over 180. It's like 0.6 radians or whatever. Probably a little more than that. A little less than that.
Wait, you would do 2 pi over 360, right?
Well, 2 pi over 360, or if you or if you factor 2 out of that, you get pi over 180, right?
Oh.
Yeah. There. Pi radians in half of a circle, all that. You have a number?
163 millimeters.
Okay, so answer 1. Okay. So answer 1 is 163 millimeters. Cool. And some of these might seem relatively large. Just keep in mind the order of magnitude of the strains that you found in the last homework assignment were really freaking small, right? Like they were tenths of millimeters or hundredths of millimeters, right? So if you kind of translate that into an angular mindset, sure, this is a relatively small angle, but like it's not a really tiny angle, like 1,000th of a degree or a 10,000th might actually be closer to equivalent with this kind of strains that we're used to seeing. I just chose a little large one on purpose. So that's where we're coming out with something that seems potentially a little large, but also just for scale, the diameter that they do give us here is about 120 millimeters. So we're a little on the high end, but not like ridiculously large. So this is like a legitimate number, a legitimately scaled number. Anyhow. Sweet. Okay, so that's the radius multiplied by 2. You get a diameter. And you can do this. It's called going down the shaft. We're not going to find. We're going to find torque in the next section. Then we're going to call it a day. So if we did all that for this first bit here, so got this is what, 226 millimeter diameter. You go up to the next pulley, and this is another torque. And we keep on going along here until we almost just barely don't get to the next pulley, another 0.7 meters away. What torque is what torque is the shaft reacting at the end now? Okay, so some combination of both of these. Since TA and TB are both going in the same direction, this end has to react what's called the combination of them both. Just like when you had, I think in the first homework assignment or second one, the column, what's called the horizontal column, with a couple different external forces acting on it, and you had to go across that column and add or subtract forces as you went across. You have to do that same thing here, but with torques. And the same way that this method of superposition let you solve a statically indeterminate system of forces, this also lets you solve a statically indeterminate system of torsions. Say that if I fixed both of these ends, because you can relate all these sections together via angle of twist, rather the sum of all the angle of twists across this length, if both ends are fixed, must be 0, or some fixed amount. I can use the same method that we used before to solve a statically indeterminate system in torsion, which we're not going to do today. Yes. Yes. Sorry. Cool. So that's all I got. Are there any questions? Yes.
If the ends were not fixed, would the same thing apply?
Would the same thing apply? What's the same thing?
Like, would the springs and stuff be the same?
Okay.
Like spinning one direction.
Okay, if it was spinning one direction or the other. If it was just free, to spin, yes, you'd still see an angle of twist in it and all that jazz, because it would still be a torque acting on different parts of the shaft. And if, say, like I had, just like a motor, and I'm just turning a shaft for fun. Maybe it has like a propeller on the end. A propeller that's generating no torque or forces. I'm just spinning it. I'm exerting some torque here, right? So if I go across the shaft, I'm still going to see an angle of twist distribution, and all that jazz. Shear stress distributions, the whole 9 yards. Does that answer your question? The only difference between this and if the ends are fixed is that here, how do I want to say this? Here I can have a finite angle of twist. That's non-zero. That's what I'm looking for. Here, if this end can't move and this end can't move, the angle of twist at each end has to not change. It can't. It's called the angle of twist here. If it's fixed, must be 0, because it can't move. Here it can be a number greater than 0. Does that make sense?
Wouldn't there be spots in the middle of that shaft on the right where it's not 0?
Correct. Just like in the middle of the stack of beams, there were points in the middle of there that had that had a finite deformation, even though the deformation of the entire shaft was 0. Does that make sense?
Yeah.
Just can't wait to see it on a homework assignment. Okay, fair enough. That's all I got. Thanks for stopping by.
So, like when you do the A and the B, when you do the R, which